Hello, everybody. Welcome back to our continuing study of geometry. Yes, I know there's something on my forehead. They're ashes. It's Ash Wednesday. Um, and then if you're liking these videos, if they're helpful for you, don't forget to like and subscribe and share. I have to say that it's YouTube. That's like the YouTube pledge, right? The like and subscribe and the YouTube salute. Thumbs up. Anyway, geometry, beauty. Uh, a lot of vocabulary. Still kind of laying the groundwork for a lot of what we're going to do. And some of this you probably already know, but we want to be really careful, really precise with our definitions so that we can build this really tight, coherent, logical structure of all these ideas that we're discovering. Actually, it's an interesting philosophical question, right? Do we discover or invent mathematics? Think about that. So perpendicular. Probably already know this. It means that there are two lines that are at right angles. So here is an example where we've got um, AC and BD, they're perpendicular. So we put this little box in there that indicates in a drawing the two lines are perpendicular. And also the shortcut for writing the two segments are perpendicular would be this thing, the upside down T. Don't forget when you do this, you got to put the line above the AC and the line above the BD because you're saying that the segments are perpendicular. If you didn't have the lines there, you'd be saying the length of AC was perpendicular to the length of BD. Lengths, numbers just by themselves cannot be perpendicular, but segments, right? Figures, shapes can be perpendicular. If two lines are coplanar and they do not intersect, then that means that they are parallel. So some examples of parallel lines here. PQ is parallel to RS. They are in the same plane, or rather, there's one plane that can encompass both of them, right? And they don't intersect. Also, UV and TW. We could also say like RS and TU. The plane that they're in is not drawn, but there would be one plane that would encompass the two of them, and they would be perpendicular, or they're parallel to each other. Um, the way that we write that segments are parallel is we just put two lines between them like this. So PQ is parallel to RS. Segment UV is parallel to segment TW. The way that we indicate this on a drawing is with little arrows. So if I want to write that PQ is parallel to RS, I do that. Those little arrows mean those lines are parallel. If I want to do that, if I have another pair of lines I want to indicate that with, I can draw a double arrow like that. Okay. And then skew lines, change of venue to accommodate a fellow teacher. Anyway, so now the concept of, oh yeah, so we can also say that parallel planes are planes that do not intersect. And so here, don't forget, we have to identify a plane using at least 3 points. So plane PQR is parallel to plane TUW, right? So this top part of the box is parallel to the bottom part of the box. So we can talk about parallel lines and parallel planes. And again, we indicate that we write it with the two lines. There's not a way that we have to indicate parallel planes in the drawing the way we do with the little arrows. Okay, what about two lines that are not in the same plane and they don't intersect? So for example, VU and RS, right? Two lines like that, they don't intersect with each other and they're not in the same plane. It's not parallel, they're called skew. So every pair of lines, either they intersect, they're parallel, or they're skew. Those are the only three options for lines and line segments. Now, we're going to put some of these ideas together into theorems and postulates. First one, I'm trying to give it a name, the intersecting parallel planes theorem. When we're citing a theorem, you can call it by its name in a lot of textbooks. In the Saxon textbook, for example, they have numbers for some of them. So you can call it by the number, you can call it by the name, or you can just state what it is that the theorem says. Okay, so this particular theorem tells us that if a plane intersects two parallel planes, then the lines of intersection are parallel. It's a lot of words. What are we saying here? So we've got two planes that are parallel. So plane D and plane M, right? It's like my initials MD. So plane D and plane M, they are being intersected by plane L here. Now, we already know from before that when two planes intersect, they intersect in a line. These line segments then of intersection are also parallel. That's what the theorem is saying. So I named it, this one I'm calling it the intersecting parallel planes theorem, because it's one plane that's intersecting two parallel planes. And what do we know? That the lines are parallel. And so if D is parallel to M, plane D is parallel to plane M. Remember, you can name planes with capital, like cursive letters. Plane D is parallel to plane M, and L intersects both planes. Plane L intersects both planes. Then MA is parallel to TH. Segment MA is parallel to TH. And yes, I made that spell math on purpose because math is awesome. Pair of perpendicular lines theorem. If two coplanar lines are parallel to the same line, then they are parallel to each other. So here are two parallel lines, or sorry, if two coplanar lines are perpendicular to the same line. So here are two lines M and T. I write my T's with a little curl on the bottom. Early on studying math and physics, I found that if I write regular T's, I would mix them up with plus signs. So I draw my T's with the little curl on the bottom. So anyway, line M and line T, they're in the same plane, and they are both perpendicular to line G. Well, if they're in the same plane and they're both perpendicular to G, that means that they are parallel to each other. Right, so that's what that means. And a lot of this stuff just makes sense. And we're not going through and proving each of these theorems, but we could, and we will later go through and prove some of these. Right, so we're just kind of building up these ideas. We introduce these new concepts, and then, okay, we have this concept. How does that relate to these other concepts, and what new ideas can we build from these? And then perpendicular to parallel lines theorem. So this is kind of going the other way. It's like um, the converse, you could say, of the other theorem. We'll talk about converse and stuff like that later. But anyway, if M and T are parallel to each other, and G is perpendicular to M, then that means that G is also perpendicular to T. And that makes sense. Okay. And it might be, again, sort of obvious, and you're like, of course. But again, we want to state everything clearly, precisely, so that we make sure everything fits together. There's no ambiguity or questions. Now, perpendicular lines theorem. Whenever we have two lines that are perpendicular to each other, what that means then is that we form the angles that are next to each other that are adjacent. Adjacent means next to. The angles that are next to each other are equivalent. They are congruent. So, TR and EY are perpendicular to each other. That means that angle TRE is congruent to angle TRY because they're both 90 degrees. Okay, and so perpendicular lines form pairs of congruent adjacent angles. And then it also goes the other way. That's this one. If we have two lines that form congruent adjacent angles, that means that they must be perpendicular to each other, right? There's no other way to do it. We have these lines. If these two angles are perpendicular to each other, they have to be 90 degrees. And all right angles are congruent theorem. Uh, there's no other way to say it. All right angles are congruent. That's the name of the theorem. That's exactly what the theorem says. Because anytime, if you have right angles, it means they have the same measure. If they have the same measure, by the definition of congruence, they have to be congruent. So all right angles, since they have the same measure, are congruent to each other. Next, one parallel line postulate. This is a postulate. This is not a theorem. And this is actually a pretty historic postulate because what we're studying here is called Euclidean geometry. So it's the geometry that was first cataloged in a textbook by Euclid, the Greek mathematician. And when he set out his geometry, he wanted to have as few assumptions as possible. He wanted to be able to prove as much as he could. The postulates are the assumptions that we set out at the beginning of our study. And this particular postulate was a postulate. It was Euclid's fifth postulate. He only had five postulates in his whole thing. We have more postulates because we're not trying to do that same kind of rigor that he had and prove everything. We're just learning it for the first time. And so what we're interested in here is how to present the information in a way that's learnable for students. But anyway, for Euclid, he only had five postulates. This was the fifth postulate. And it says, through a point not on a line, there is one and only one line through that point that is parallel to the line. So here's point O and line R. If I want to draw a parallel line to R through O, there's only one line. I can't draw multiple lines through O that are parallel to R. Okay. Now, Euclid wanted to be able to prove it, but he couldn't. And so he had to include it as a postulate. And people for years, centuries, actually tried to prove Euclid's fifth postulate. Later on, some mathematicians tried a method of proof called reductio ad absurdum, where they actually assume it to be false. Well, okay, let's assume it to be false, and then we'll get a contradiction later on. But when they did that, they ended up actually inventing different kinds of geometry. They invented spherical geometry and hyperbolic geometry. That's totally different subject. Those are non-Euclidean geometries. In other words, the surfaces that you're working on, you can think of it this way, are not flat plane surfaces. So Euclidean geometry is flat plane surfaces where this postulate is true. Again, it's postulate, it's not a theorem. Okay, transitive parallel lines theorem. If you have two lines that are parallel to the same line, then they are parallel to each other. Okay, the transitive property of equality, for example, is that if A equals B and B equals C, then A equals C. It's the same kind of idea with parallel lines that we can use. If two lines are parallel to each other, or to the same line, then they're parallel to each other. And so we have here, right? So PQ is parallel to RS, but PQ is also parallel to TU. So TU and RS are both parallel to PQ. That means then that they are parallel to each other. Now, you might be saying, well, if they're parallel, they have to be coplanar. And there's not a plane here that includes the two of them. And the answer is that there is a plane, but we're just not seeing it. It hasn't been drawn. We could draw it if we wanted to, if you're so demanding for that sort of thing. All I have to do is include some lines here. And now I have plane RSUT or plane RST that does encompass those lines. Okay. And so that's it. That's the whole lesson. So really focusing in on perpendicular and parallel and those two concepts and applying them in a bunch of ways and coming up with some theorems that we know are true based on those concepts. Thanks for watching. I'll see you next time. And again, don't forget to like and subscribe.